Hi, this is Nathan, and for the next example on MLE, I want to do the exponential distribution. So, each marginal PDF, we're doing the continuous case this time, is 1 over theta e to the negative xi over theta, right? Now, the joint PDF of our sample of n IID, independent and identically distributed exponential random variables, it's going to be the product from I equals 1 to n, 1 over theta e to negative xi over theta. And since this is the joint PDF, this is the likelihood function we have. So now if you take the log of this, we get the log likelihood function, which is equal to the sum from I equals 1 to n of ln of the PDF, right? Which is equal to the sum from I equals 1 to n of ln of 1 over theta plus ln of e to negative xi over theta. Natural log of this, note that 1 over theta is equal to theta to negative 1, so ln of these is equal to negative 1 ln of theta, right? Plus, now natural log of e to any power, the ln and the e will cancel out with one another. So we have negative xi over theta, right? Before I take the derivative, I'm going to distribute in this summation. So we have negative n ln of theta plus sum of negative xi over theta, right? Now we're taking the derivative with respect to theta this time because theta is the unknown parameter that we're estimating. This is going to get us negative n over theta plus sum of xi's over theta squared, because the derivative of 1 over theta is equal to negative 1 over theta squared, right? So now we set this equal to 0, and we have 0 equals negative n over theta plus sum of xi's over theta squared, or we can add this over and get n over theta is equal to sum of xi over theta squared, multiply the denominators up, and we get n theta squared is equal to sum of xi theta, or divide by theta, we get n theta is equal to sum of xi's, or divide by n, and this gets us theta hat, using the maximum likelihood estimation method, is equal to sum of xi's over n. And again, this makes a lot of intuitive sense, because for the exponential distribution, theta is equal to the mean, right? The expected value. So it makes sense that the maximum likelihood estimator for theta is sample mean. But another way to parameterize the exponential distribution is using lambda instead of theta, right? So if you use that instead, you have lambda is equal to 1 over theta, right? Then the PDF is equal to theta e to negative xi lambda. Or the joint PDF, which is the likelihood function, is the product of n IID exponential distributions with lambda instead of theta, right? So the log likelihood function is the sum of the log of lambda e to the negative lambda xi, which is equal to sum of log of lambda plus log of e to negative lambda xi, which is equal to the sum of log of lambda plus negative lambda xi, right? Now we take the derivative of this with respect to lambda, and we get sum of 1 over lambda plus negative xi, or distributing in this summation, we get n over lambda minus sum of xi, and since we're finding the maximum, we took the derivative. Now we set it equal to 0. This gets us n over lambda is equal to sum of xi, or multiplying lambda divided by sum of xi's, n over sum of xi is equal to lambda hat MLE. And if you look, we have lambda hat MLE is equal to 1 over theta hat MLE. And we have lambda is equal to 1 over theta. Turns out this property of maximum likelihood estimators is true more generally than just in the exponential distribution. So we can write, if lambda, a parameter, is equal to f of theta, some function of theta, in our case we have 1 over theta, then lambda hat MLE is equal to f of theta hat MLE. So we have, if lambda is some function of theta, then lambda hat MLE is the same function of theta hat MLE.